All right, today we're going to be talking about polar coordinates and polar graphs. Since this is a new thing, I just want to say that what we're going to be doing is I want you to have your PDF of the notes, class notes that are on the Lessons tab at MyTCC, the Blackboard. And have those in hand and watch this video and work along with me as we go through this. I do want to say that I'm not going to read everything to you, so make sure you're reading the things in between what I'm talking about. So do be aware of that. All right, so we're used to working with a rectangular coordinate system where when we want to go to any point in the plane, the XY plane, we start at the origin and move so many units to the right or left and so many units up or down. So this point that I've arrived at is 3 to the right of the origin and 2 below the origin. So we call the coordinates 3, -2. So it's ordered because it's horizontal movement, comma, vertical movement. That's what we're used to. Now, we've used this in regular graphing and in trig and all those things, and we've also used this same system in the parametric form. What we're going to study today is a coordinate system called the polar coordinate system. The difference is that instead of an origin, we have a point called the pole, and instead of 2 axes, we have 1, and this axis is actually a ray. Well, it's supposed to be straight. Excuse my inability to draw straight today. That's what we call the pole, that point, like the origin. And this ray is what we call the polar axis. And notice it extends to the right from the pole. It's kind of like the positive part of the x-axis. And in this system, when we're trying to find a point in polar coordinates, we're going to have 2 different pieces of information, not horizontal and vertical motion from the origin, but instead an angle from the polar axis, measured just like we did in pre-calculus. So positive is counterclockwise and negative angles are clockwise. And we could use, by the way, radians or degrees. We'll probably pretty much stick with radians here. And the other part of the coordinate is how far you are from the pole. So let's say we have a point right here. If I were to draw a ray from the pole through that point, then the angle from the polar axis will be measured, and we'll call that theta. And the distance from the pole to our point will be r. And so the coordinates of this point involve those 2 variables. The order in which we put those is always r, then theta, r theta. All right, so that's the basic introduction of the polar coordinate system. The r, by the way, is a directed distance. So this is a big difference from what we're used to seeing with our normal r when we were in trigonometry. R was always positive. In this particular world, the polar graphing world, R can be negative, and that is a major difference compared to what we learned before in pre-calculus. All right, so if you look at the figure 10.36 in your notes, you'll notice that that point for A is from the polar axis, move pi/3 in the counterclockwise direction, and go out from the pole by 2. Notice the concentric circles here. Instead of having a grid like we would have if we drew in more than what I did here, but if we drew in some dotted lines where those values are, we would have rectangles. So here's, for example, a rectangle. And ideally that rectangle is a square if we want things to look non-distorted. We would like for that rectangle to be square. But anyway, in other words, this is what we call the rectangular coordinate system, because the grid is rectangular. Ideally squares, but that's not always possible. So the grid for the polar graphing is, notice we have a pole and a bunch of concentric circles, kind of like the tick marks on the X or Y axis, showing distances from the pole. And so we can go from the pole, which I'll go ahead and draw in here, around, say, 2 pi over 3, which is about right there, and we can go out from there 2 units. Did I say 2 pi over 3? I meant pi over 3. Excuse me. Pi over 3. And we can go out from the pole 2 units, which means we're on the second concentric circle out from the pole. And that lands us at the point 2 pi over 3. And of course the grid in the notes looks a whole lot better than mine, so please refer to that. But that's basically how we could draw those. An interesting thing is if I were to ask you to look at that point, the very first point I had you look at, and say, what are the coordinates of that point? There's only one correct answer. To go from the origin, you have to move 3 to the right and down 2. So the coordinates of that point would have to be 3, -2. But if you look at B and C, those are actually the same point with 2 different names. The reason for that is that as you learn in trigonometry, we have something called coterminal angles, and the angle -pi over 6 is coterminal with 11 pi over 6. Remember, coterminal angles are separated from each other by multiples of 2 pi. So -pi over 6 plus 2 pi gives you 11 pi over 6. The other thing that could be done for that same point, not what they did in either case, but if they had, let's see, whoops, change color. If they had gone in that case, let me draw this really fast, sorry. Sorry for the non-perfect circles. Luckily there are machines that generate better things than what I'm doing. If I wanted to name this point, I could use, as they did, 3 -pi over 6. I always do the angle first when I'm graphing. So from the polar axis, go clockwise pi over 6, and then from the pole out 3. And that's where that red dot is on the second polar graph, as you see in part B of figure 10.36. Or we could have gone all the way around from the polar axis counterclockwise, 11 pi over 6, and gone out 3. Those are kind of 2 good answers that we might want to focus on, because a lot of times, because there are infinitely many different ways we could represent that point, we usually want to stay with 1 of 2 systems, either from 0 to 2 pi. So all of the angles we could use there would be restricted to the positive ones, or go from -pi to pi. And that allows us to find answers, both positive and negative, that are closest to 0. And so those are 2 systems that might be used. So the 11 pi over 6 fits within the first system, 0 to 2 pi, and -pi over 6 fits within the second system, -pi to pi. Now, there are other possibilities. What if I were to have gone with this ray right here. And let's see, what would that measure? I believe that would be 5 pi over 6. 5 pi over 6. That sounds right. And instead of going along that ray in the positive direction from the pole along that ray, if I were to go in the negative direction, so let me change color so you can kind of see how this is different. If I were to go in the negative direction along the ray pointing the opposite direction, I could land on that same point in red. So the coordinates of that point would then be determined to be, since I went in the opposite direction from the ray that terminates at 5 pi over 6, that would mean that I use a negative 3 for the r paired with 5 pi over 6. And of course, negative 3 could be used paired with any angle coterminal with 5 pi over 6. So, in other words, the rectangular system, if I plot a point and ask you to find its coordinates, there's only one answer. But if I plot a point in polar coordinates, there are an infinite number of answers. You could have a positive r and have the ray terminating going through that point, or it could be pi away from that, the other side of the line. So how I got 5 pi over 6 was negative pi over 6 plus pi puts me exactly on the other side of that line. And using that ray and going backwards to get to the point, that implies I'd have a negative r. So as practice, and I really wish I had that grid here on my machine, but I don't, unfortunately. So looking at that grid that they give, it's actually easier to do there. Let me just try to draw something similar to that. Now, to make it easier, a lot of times, although there's only one polar axis, what we end up doing is drawing a lot of different radial lines. One common way to do that is, like showed here, please look at the one online. It's better. If we go 1, 2, 3, 4, 5, 6 regions from 0 to pi, means each one of those is 1, 2, 3, 4, 5, 6. Yeah. So from 0 to pi over 2, excuse me. From 0 to pi over 2, if we divide that into 6 equal pieces, each one of those is a movement of pi over 12. And if you use multiples of pi over 12, you'll include every special angle that ends up relating to a 30, 60, 90 right triangle or a 45, 45, 90 right triangle, and some extras that you're not used to seeing. So one of the first things you want to do when you get a polar grid is to determine, for the radial lines that they have, what angle is represented from one radial line to the next, as I just did. A lot of times those radial lines, especially if they allow for r values that are big at all, they may not extend all the way to the pole to avoid confusion, because it'll become so cluttered at the pole if you do that. So, so let me actually answer the question that was posed for that example. It does take me a while to move down the page, so I apologize for this slow movement. And hopefully you're doing this on your printed out page. All right, so anyway, here we go. So I'm going to make several circles. And if you look at the R values, if you're doing this by hand, look at the biggest R and then make sure you have circles out to that value, at least. All right, so for 3 pi over 4, I'm going to go to 3 pi over 4, which is this ray right here, and go out along that ray 1, 2, 3, 4. So there's the point for 3 pi over 4. we're supposed to write two other pairs of polar coordinates for each point, one where r is positive and one where r is negative. So let's go ahead and do that before we go to the other point that we're working with. So if I want it to be a positive r like it is to begin with, I'm going to keep the 4 positive. I need a coterminal angle with 3 pi over 4. You can add 2 pi, subtract 2 pi, add 4 pi, subtract 4 pi, infinitely many things you could do. I'm going to ask that you not go crazy on me and either add 2 pi or subtract 2 pi. Most people find addition easier, so that's what I'm going to do, generally speaking. 2 pi is 8 pi over 4 plus 3 pi over 4 gives me 11 pi over 4. Now, if I want to have a negative r, that's going to involve thinking about having a ray pi away from that one, this I just wrote in yellow, and using negative r's for that yellow ray to get to the point that's in green. Excuse me. I'm gonna mute my phone. It's going off here too much, so apologize for that. All right, here we go. So we need to find a designation for that ray. We can get from the ray we started with, 3 pi over 4, we could add pi or we could subtract pi. We could add 3 pi or subtract 3 pi. So any odd multiple of pi added to the original angle will get us a valid ray, the yellow ray. So it doesn't really matter to me what we do. If I subtract pi, I'll get, excuse me, made a little stray mark there. If I subtract 3 pi, I'll get negative pi over 4. And again, there are infinitely many correct answers. The way that this is generally going to be done is you're going to encounter problems, and I'm going to say, I want you to give me a positive r and an angle between this and that. And so it won't be like you have infinitely many choices. In most problems, it'll be not everything possible. All right, so let's do the other one. Let's see, that r is 6, so I've got to go a little bit further out this time. Wow, those circles look awful, don't they? 1, 2, 3, 4, 5. One more. Oh, maybe this one will be my best one yet. Okay, so using the angle is 7 pi over 6, just right here. Then the r value is negative, so instead of using a point on that ray, I'm going to go behind that ray into the first quadrant and put my point at a value of 6 away from the pole in the negative direction from the angle given, 7 pi over 6. So that green dot right there is a plotting of the point in polar coordinates, negative 6, comma, 7 pi over 6. I'll be honest with you, using negative r is not something I would say is the best unless the directions say otherwise. Positive r is always going to be an easier call. All right, so looking at that point, I'm actually tempted to do a positive 6 first, because that's one of those rays that I think I can identify very quickly. That yellow ray is exactly pi away from the red one, and so if I subtract pi from 7 pi over 6, I'm at pi over 6, and so one of the coordinates of that point could be 6 pi over 6. Now if I'm keeping negative 6, that means I'm using the red ray or anything coterminal with it. I can take that 7 pi over 6 and say add 2 pi. 2 pi would be 12 pi over 6 plus 7 pi over 6 is 19 pi over 6. Okay, so You can see on the next page that there are some general formulas that if you keep r the same, you can add any multiple of 2 pi to the angle to get an alternate name for that point. Or you could change the r to its opposite and take your original theta and add an odd multiple of pi. The other thing that's on that is that the pole is a radius of 0, so any angle can be used with that. So 0 pi, 0 pi over 2, 0 pi over 6, those are all coordinates for the point called the pole. Now, if we look at the next pages, the focus on these next few pages is on converting from one system to the other. So you might have something in rectangular that you're worried about. Well, what are the polar coordinates for that same point? It's assuming you could superimpose one grid on top of the other, or vice versa. So one of the things that we're going to have to do is take something that's in the form xy and convert it to r theta, or something that's in r theta converted into xy. So these are the two tasks we're going to have, is to do that conversion. So if I have x and y, let's do that first. If I have x and y and I'm trying to find r and theta, we need to find a relationship amongst those things. So if I were to draw a triangle, kind of like what we did in trig, where x is this leg of that right triangle and y is this leg of that right triangle, r is the hypotenuse, and the angle is theta. So if we know x and y, what could we use to find r? Well, since those are the three sides of a right triangle, we know that the Pythagorean theorem applies. So x squared plus y squared equals r squared. If you know x and y, you could use this equation to solve for r. Then, what's the relationship, if you know x and y, for theta? Well, because it's a right triangle, we know that there are trig relationships that are defined in terms of ratios of two sides of a triangle. The tangent of theta, if you'll recall, is opposite over adjacent, which would be y over x. So again, if you know x and y, you could find theta using this equation. Now, going the other way, if I know r and theta and I'm asked to find x and then find y, you might remember there are some other relationships that involve, let's say, r theta and just x. If you look at the triangle, x and r and theta, x would be adjacent, r would be a hypotenuse. So the relationship there is that the cosine of theta is x over r, and the sine of theta relates y and r to each other. So if we want to solve for x, we could multiply both sides of the equation by r. So x is equal to r cosine theta. And doing the same thing with the other equation, y is r sine theta. So these are the two equations you'll need if you're converting from polar to rectangular. You know r and theta, and you're trying to find x and then find y. And then these two equations are the equations that will take us from rectangular to polar. If you know x and y, you need to find r, and then you need to find theta. And these are the two equations that will allow you to do that. You certainly need to memorize these equations and have them at your disposal. All right, so let's go from polar to rectangular for our first example. Let me move this down again. For example 1, part A, we have the polar point 2, pi. And we're supposed to convert that to rectangular coordinates. Alrighty, so for part A, we're given polar coordinates 2, pi. Well, using the equations that we have in green, that implies that x will equal r, which is 2, cosine of theta, which is pi. Cosine of pi is -1. 2 times -1 is -2. By the way, you may need to go back and review some of your trigonometry, because things like what's the cosine of 7 pi over 6 or what's the sine of 3 pi over 4 will occur, and you will need to know those values and how to get them. So some of you, that means going back to your right triangles and figuring out again. Make sure you have those in your head. And some of you, that means pulling out your unit circle and getting that back in your head. All right, anyway, y is r sine theta, so r is 2. Sine of theta, which is pi. The sine of pi is 0. 2 times 0 is 0. So the rectangular coordinates are, therefore, -2, comma, 0. Right. So for part B, we're going from polar to rectangular again. So part B, the given coordinate is square root of 3, comma, pi over 6. So again, using the green equations from above, x is r, square root of 3, cosine of theta, which is pi over 6. Excuse me. Pi over 6. All right. And we'll go ahead and finish that out. So cosine of pi over 6 is square root of 3 over 2. And that simplifies to be 3/2. Okay. Now y is r sine of theta, so square root of 3 sine of pi over 6. The sine of pi over 6 is 1/2, so this will be square root of 3 times 1/2, which is square root of 3 over 2. So that means that the rectangular coordinates for this point are 3/2, comma, square root of 3 over 2. All right. So, very good. Got that one done. Let's see. And it's probably a good idea for you to maybe, let me go back a second. I'm sorry. I just had this thought. It's probably a good idea for you to look at those points and make sure that makes sense to you, where that point is each time. So, pardon me for going back, but this point, if we use the ray that's pi, that'll be this ray right here. And if we go out from there, 1, 2, I'm not drawing the entire circles. Go out from there, 1, 2. That puts us at this place as far as a polar coordinate. And if you think about the xy axes, that of course is a point that's at -2, 0. The next one's a little bit more challenging because we have fractions and radicals and all kinds of stuff going on here. Not impossible, just more challenging. Okay, so if we have an angle of pi over 6, oops, well, I made that a little bit small looking, sorry about that, and go out along that square root of 3 units. So square root of 4 is 2, square root of 1 is 1, so square root of 3 has to be somewhere between 1 and 2. I'm going to say it's about right there. Okay, and then this is, like I said, a little bit harder to see. If I were to go on here and kind of complete those circles, that's where 1 would be, and that's where 2 would be. Whoops, that's not quite right. that would actually circle to be about right there. So a little bit more like that. So although I'm graphing without the benefit of graph paper, that should make sense if that's about 1.5 to the right. Remember I said that angle is a little bit small. And up square root of 3 over 2, which is about 0.9-ish. And 1 would have been about right here. So that sort of makes sense. As long as it makes sense, you're not like in the wrong quadrant or something. That's what I'm trying to avoid, is that you get into the wrong quadrant accidentally. And it's just a nice double check on what we're doing. All right, so that's actually a really good place to stop. I'm going to pick up with another part in this series of lectures. And so I'm going to close this off and move to the next